Welcome to EPG Pathshala lectures on numerical methods. Earlier we have seen several techniques for interpolation like Lagrange interpolation, Newton's divided difference interpolation, then interpolation with equally spaced nodes, and several techniques of these interpolation methods have been discussed. In this module number 7 on interpolation, we will be talking about inverse interpolation. Inverse interpolation is nothing but we are now so far we were given the data nodes and y was a function of x, and for a given value of x in the interval of observation, we are trying to estimate value of y. In the inverse interpolation, we will be doing exactly the reverse, that we will be looking for given y, we will try to find out what kind of x we will be getting, what will be the estimate of x corresponding to that y will be given. In interpolation, given the data points xi, yi, I equal to 1, 2, 3 up to n, one estimates values of dependent variable y at some intermediate value of x. For example, if x represents time and yx represents the distance travelled by a car in time x, thus y's are the distances travelled by a car in times xi's. Then in interpolation, one attempts to estimate distance yx travelled in time x in the domain of observation. However, quite often one may need to find at what time car has reached a particular spot at a distance y within the minimum and maximum distances y1 to yn. The technique of finding an estimate of a value of an independent variable x corresponding to a given value of the dependent variable within the range of the observed values of y is called an inverse interpolation. As another example, population census of a country is taken after every 5 to 10 years, say in 1995, 2000, 2005, 2010 and 2015, and suppose the government wants to know that exactly at what point in time the population has reached a specific level. To answer such queries, one has to use technique of inverse interpolation. At the outset, it appears that the inverse interpolation can be achieved by interchanging the role of independent variable x and dependent variable y and interpolating x on data points yi, xi instead of xi, yi, I equal to 0, 1, 2, 3 up to n. However, this may not be feasible unless the observed values of y, namely y0, y1, y2, y3, yn are distinct, as almost all interpolating techniques require that the interpolating nodes be distinct. In observing any process involving an independent variable x and dependent variable y, it may be possible to impose some conditions like distinctness of values on the independent variable x, but values of y depend on the process being observed and no control can be exerted on the values of y. Thus, this particular approach for implementing inverse interpolation can be used on the processes for which distinctness of values of x ensures distinctness of the corresponding values of y. Most probably this will be possible only when the function is one to one in the domain of observation. And in this case, one can use either Lagrange or Newton's divided difference interpolating formula. This is illustrated in example 1. Given the following data points, say x equal to 0, 0.0, 0, 0.5, 1 and 2, and corresponding values of yx are 0, 0.57, 1.46 and 5.05, and we want to find out estimate the value of x when y is equal to 0.5. So, here we are given y and we are trying to estimate x. So, by Lagrange interpolating formula, we can approximate the function x of y. Now, I am not saying y of x of y by a polynomial of degree 3 on the y interval 0 to 5.05. Using the 4 data points given in the above table as xy equal to 0.0, L30y plus 0.5 into L3 comma 1 of y plus 1 into L3 comma 2y plus 2 L3 comma 3y. So, here Lijy is a Lagrangian interpolating polynomial. So, these are the characteristic polynomials in the Lagrange interpolation formula that we used earlier, but here these are the functions of y and we are using as coefficients the values of x there, xi's. So, thus xy will be given by 0.5 because 0 into 0, first term will be 0 anyway because you are multiplying it by 0. So, everything will be 0. So, first non-zero term will be 0.5 into y minus 0, y minus 1.46, y minus 5.05 divided by 0.57 minus 0, 0.57 minus 1.46 and another factor is 0.57 minus 5.05. And next term will be plus 1 into y minus 0, y minus 0.57, y minus 5.05 and 1.46 minus 0, 1.46 minus 0.57 in the denominator, all these factors. So, 1.46 minus 5.05 and third term will be plus 2 into y minus 0, y minus 0.57, y minus 1.46 in the numerator divided by 5.05 minus 0, 5.05 minus 0.57, 5.05 minus 1.46. So, you can see that we have interchanged the rule of x and y in this particular formulation. So, putting now y equal to 0.5 in this, we get desired estimate of x of 0.5 and after due manipulations we can see that x of 0.5 will be equal to 0.44717. Since 0.5 belongs to another interval 0.0 and 0.57 also, we have an option of approximating x of y by linear Lagrange interpolating polynomial on the y interval of 0.0, 0.57 using two data points 0, 0 and 0.57, 0.5. So, in this case xy will be equal to 0.0 into y minus 0.57 upon 0.0 minus 0.57 plus 0.5 into y minus 0 upon 0.57 minus 0 and this will give you estimate of x at 0.5 will be equal to 0.4386. So, this is another estimate. This we have already done in the case of interpolation, that we have interpolated or estimated value of x using different interpolating polynomials. Here also we are doing the same thing, and similarly I can use this, since 0.5 is in the interval 0.1.46 also, hence we may approximate x of y by quadratic Lagrange interpolating polynomial on the interval 0 to 0, 1.46 using three data points now here 0, 0, 0.57, 0.5, 1.46, 1. Thus, we have x of y equal to 0.5 into y minus 0, y minus 1.46 upon 0.57 minus 0, 0.57 minus 1.46 plus 1 into y minus 0 into bracket y minus 0.57, 1.46 minus 0 and 1.46 minus 0.57, and hence in this case the estimated value of x at 0.5 is 0.44615. Note that the different interpolating polynomials gives different estimates for x of 0.5. Comparison of these polynomials is shown in the figure 1, and we can see that this figure 1 is the first part of figure 1, that is A, is the linear Lagrange polynomial we are given, and we can see that at y equal to 0.5 x value is 0.4386. Similarly, if I take quadratic interpolation, so this figure shows again the another estimate, y is equal to 0.5, we get x equal to 0.4462, and similarly in the cubic interpolating polynomial, if you take at y equal to 0.5, I get x equal to 0.4472. We could have also used Newton's divided difference interpolation formula in place of Lagrange interpolation formula in the above example. However, in that case divided differences of x over y must be computed first. One may also use graphical representation of interpolating polynomial px estimating y in terms of x. To implement inverse interpolation to estimate x for a given value of y as shown in figure 2. It can be observed from the figure 2b that in case when y as a function of x is not 1 to 1, the graphical method may give multiple estimates of x for a given value of y. Let us see the figures now. You can see that figure 2a gives me a kind of a 1 to 1 function, and therefore for a given value of y we have estimated value of x. There is only one estimated value of x. And if you look at the figure 2b, you can see that this is not a 1 to 1 function, and we can see at this, if I take y equal to 0.5, and I will have multiple values of x which are estimated from this figure. So that is the drawback here. That means instead of getting only one estimate of x, we are getting 4 different estimates corresponding to one single value of y. So what we need is a more systematic approach for interpolation, inverse interpolation, and we use here method of successive approximation for inverse interpolation. So suppose n plus 1 data points xi, yi, I equal to 0, 1, 2, 3 up to n are given, where x0, x1, x2, x3, xn are equally spaced, and it is required to estimate the value of x for a given value of y. Now this particular method of successive approximation is applicable when x values are equally spaced. As seen earlier, the Newton's forward difference interpolating polynomial over these equally spaced nodes for finding out y given x is given by px equal to y0 plus s into delta y0 plus s into s minus 1 upon 2 factorial into delta square y0 up to s into s minus 1 into s minus n plus 1 upon n factorial into delta raised to n, that is nth forward difference at y0, where s is nothing but x minus x0 divided by h. So s is a new variable that we introduce, which has a relationship with x as s equal to x minus x0 divided by h, and we use this polynomial in terms of s. This polynomial px is being used to estimate y for given x. This involves computation of the right hand side of equation 1 for given x. In inverse interpolation by the method of successive approximation, the same polynomial px is used to estimate x for given y. This amounts to solving the equation y equal to px for s first, because it is in terms of s only, and then estimated value of x will be given by x0 plus estimated value of s into h. So for solving the equation y equal to px for s, we use the method of iteration as described earlier. For this purpose, rewrite the equation 1 as follows. So what we are doing is we are writing s in terms of remaining terms of s. So s equal to 1 upon delta y0 into bracket y minus y0 minus s into s minus 1 upon 2 factorial into delta square y0 minus dot 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 minus s into s minus 1 dot 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 s minus n plus 1 upon n factorial into delta raised to n y0. This is what we will get. We use equation 2 recursively to compute successive approximations Sm to the estimated value of s, and the first approximation for this will be using the first term only, and S1 will be given by 1 upon delta y0 into y minus y0. So that is my first approximation. When I am considering the second approximation, I will use this value of S1 in the remaining terms, because now s has to be written here. So the estimate s value on the right hand side will be s equal to S1. So thus second estimate S2 is given by 1 upon delta y0 y minus y0 minus S1 into S1 minus 1 upon 2 factorial into delta square y0. So we are using two terms on the right hand side, and in these two terms if s appears, we are using s equal to S1 to find out the second estimate of s. Similarly, third estimate of s is obtained by using three terms on the right hand side, and now using latest estimate S2 for s in those terms. So we get S3 equal to 1 upon delta y0 into y minus y0 minus S2 into S2 minus 1 upon 2 factorial into delta square y0 minus S2 into S2 minus 1 up S2 minus 2 upon 3 factorial into delta cube y0 will get. And similarly, the fourth estimate or nth estimate can be obtained by using all the n terms on the right hand side and using the latest estimate, that is n minus 1th estimate, n minus 1th estimate of s in place of s in all those terms. So, thus I get Sn equal to 1 upon delta y 0 into bracket y minus y 0 minus Sn minus 1 into Sn minus 1 minus 1 upon 2 factorial into delta square y 0 minus dot dot dot, and last term will be Sn minus 1 into Sn minus 1 Sn minus 1 minus 1 dot 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 Sn minus 1 minus n plus 1 upon n factorial into delta raised to n up y 0. So, delta raised to n is the nth forward difference at y 0. So, this is what your estimate. So, these are the successive approximation to the values of s, and now using these successive approximations we can find out the value of s. Now, what we do, when to stop this process of finding out successive approximations. So, and for some m greater than n, I get Sm equal to, we will be getting Sm equal to this. Now, if m is greater than n, there are no more terms there. So, only we will be using n terms only for estimating, but every time we will be changing the estimate of s to be used in place of s. So, for m greater than n, we will be using Sm as 1 upon delta y 0, y minus y 0 minus Sm minus 1 into Sm minus 1 upon 2 factorial delta square y 0, and we will continue this till the nth term, and that is Sm minus 1, Sm minus 1 minus 1, Sm minus 1 minus n plus 1 upon n factorial into delta raised to n y 0. So, we are using up to nth divided nth forward difference only. The process continues. So, we can continue this process as long as we wish. So, when do we stop this process of estimating s? And we stop until we continue until Sm is equal to Sm minus 1. So, if two successive estimates of s are close to each other, close enough to each other, then we will stop this process, and the last estimate will be used as the estimated value of s, and then the estimated value of x can be obtained using this estimated value of s as x equal to x 0 plus h Sm. So, what we have seen here is that we are computing estimate of s first. For that we are using term by term, that means up to n, there will be up to n, there are n terms on the right hand side. Though in the first estimate we will use one term, in the second estimate we will use second term, in the nth estimate we will use all the nth term. And when we are considering the nth term, we are using n minus 1th estimate of s on the right hand side. After n term, there are no more terms available. So, we continue using only those n terms, but we go on changing the estimates of s on the right hand side, and that is how we get for any general m greater than n estimate of Sm, and after that we continue this process till we get Sm equal to Sm minus 1. That means two consecutive estimates of s are close to each other, and once we get that, we use that estimate of s to find out the estimate of x. We will see the example for this. So, a car traveling along a straight road actually is clocked at a number of points. So, that means we are taking periodic observations of that. The data from the observations is given in the following table. Then at what point in time the car passes 250 kilometer mark? That is my question. That is what I want to find out. The table gives me in hours. So, time in hours is 0, 2 hour, 4 hour, 6 hours. So, that means within these many hours we are trying to observe the movement of the car. The distances in kilometer observed at 0 is 0, at after 2 hours is 125, after 4 hours is 270, after 6 hours it is 400 kilometers. The first we find out the forward difference table and compute that formula. So, for forward difference table we are finding out tabular form we are using here. So, if in the first column we give xi values 0, 2, 4, 6. In the second column we give distances yi which are already observed. So, 0, 125, 270 and 400. Then the third column gives me first difference. So, 125 minus 0, that is 125, 270 minus 125 is 145, 400 minus 270 is 130. Then the fourth column gives me second difference, forward difference, that is 145 minus 125, that is 20, and 130 minus 145, that is minus 15 we get, and then last column gives me the third forward difference, and that is minus 35. So, minus 15 minus 20. So, we get this minus 35. So, this gives me the forward difference table. From this forward difference table now we will be using, and we are using that for the formula which we already explained earlier, to find out estimate of S first. So, for given value of y as 250. So, I am using now S1, which is y minus y0 we are taking. So, y minus y0, y is here 250, y0 is 0. So, 250 minus 0 divided by the first difference, that is 125 we are taking, and that is 125, and that is the first forward difference at point 0, and that is, this gives me estimate S1 as 2. Use this estimate S1 on the right hand side and find out S2 as 250 minus 0 minus 20 into 2 minus 2 minus 1 upon 2 by 125, and the whole thing divided by 125 we are considering, and that is how I will get this estimate of S2 as 1.84. Similarly, I am doing S3, it's the third estimate we are trying to find out, that gives me value 1.865, and we are finding out fourth estimate as 250 minus 0 minus 20 into 1.865 into 1.865 minus 1 and divided by 2 plus 35 into 1.865 into 1.865 minus 1 into 1.865 minus 2 divided by 6, and then whole sum is divided by 125, that is delta y0, and that is equal to 1.861 after simplification. S5 again we are using here the same number of terms, but now we are using estimate of S as 1.861, which is obtained by latest, and if I use the same formula I will get 250 minus 0 into minus 20 into 1.861 into 1.861 minus 1 by 2 plus 35 into 1.861 into 1.861 minus 1 into 1.861 minus 2 divided by 6, and then whole divided by 125, and again we get estimate as 1.861 if we approximation up to 3 decimal places, and you can see that the estimate S4 and S5 are almost identical and correct to 3 decimal places, and therefore we stop our procedure and we take this last estimate of S as our final estimate of S, and from that we get for y equal to 250 the estimated value of x as 0.0 plus 2 times 1.861, and that is equal to 3.722 hours. So, this is how we can get the inverse interpolation. Now, we look at the computational aspect of this particular algorithm. Given the points xi, yi, I equal to 0, 1, 2, 3 up to n with x0, x1, x2, x3, xn as the equally spaced interpolating nodes, to inversely interpolate the value of x for given value of y, one has to evaluate up to nth order forward differences over these nodes as we have seen in the example, and then apply the method of successive approximation. The algorithm for this purpose is as follows. So, we are writing down the algorithm. So, algorithm inverse interpolation, that is IIP, method of successive approximation, that is MOSA. So, we are given short name to the algorithm as IIP dash MOSA. Input is n and the data points xi, yi, I equal to 0, 1, 2, 3 up to n, such that x0, x1, x2, xn are equally spaced with step size h equal to x minus x0, and y belonging to AB at which we would like to estimate x. So, where A is equal to minimum of the observed values of y, that is y0 to yn, and B is the maximum value of y, that is y0 to yn. Maximum number of iterations here, that is max iter, because we are not very sure that whether within those iterations you will get the convergence or not. So, we always take a maximum number of iterations as advance as a measure for to ensure that the algorithm does not enter into an infinite loop. So, maximum number of iteration I denoted by a max iter, and this we are taking it as input, and normally that will be taken greater than n. The required accuracy, that means how much accurate you want the results to be, for that we are considering epsilon. So, if we take the 2 successive approximations are less than this epsilon, we will stop the algorithm. And output which we obtained from this algorithm is the successive approximation says 0, S1, S2, Sm, and estimated value of x as xc. So, these are the outputs that we are going to get. The algorithm is the first we evaluate the divided differences FDKI, which denotes the kth forward difference. So, we will estimating forward differences FDKI, which denote the delta k fxi, that is kth forward difference of f at point xi, and k equal to 1 to 3 up to n, and 0 runs from 0 1 to 3 up to n minus k, and these forward differences can be computed iteratively as follows. This we have done it in the module on equally spaced interpolation also. So, for I equal to 0 to n, fd0i is your values of yi, and iterative steps gives me the further divided differences. So, for k equal to 1 to n and for I equal to 0 to n minus k, we find out fdki as fdk minus 1 at I plus 1 minus fdk minus 1 comma I. This is what we will be getting. So, this will be your iterative step, and then we compute the successive approximation. So, the next step is this. So, let Sk be the one dimensional array of successive approximations, say of dimension 100. I am taking it as dimension 100, assuming that max iter will not be more than 100. So, k that is the first term, that is k, is taken a capital K as constant, which is given by y minus y0. S1 will be now k upon fd1 comma 0, that is the first divided difference at 0, and we are taking flag equal to 0. So, this flag will be deciding whether you are coming out of the algorithm after completing maximum number of iterations or after getting approximation. So, flag equal to 0, and then we are taking for I equal to 2 to max iter, we are computing this sum on the right hand side. So, sum equal to k, s equal to si minus 1. So, we are using the latest estimate of s here, and term we are finding out each term, and then we are adding that term to the sum. So, we are getting term as for j equal to 2 to minimum of I comma n, we are considering term equal to term star s minus j plus 1 divided by j. Nth term, there will be no more terms to be added. So, we will be getting only this, and then equal to sum plus fdj comma 0 star term. So, this is what we will be doing, and then final si will be equal to sum divided by fd10. If two successive estimate, that is s is the I minus 1th estimate and si is the ith estimate. So, if these two successive estimates are difference, their difference is less than epsilon, we will say that flag is equal to 1. So, when flag is 1, we are coming out after convergence is achieved. So, then in that case we will take m equal to I and exit. In case if flag is equal to 0, when you are completing those for that for loop, we will say that if flag is equal to 0, we will get m equal to max iter, and will print that message that successive approximation do not converge in 100 iterations, and that is how we will get. But last estimate that we obtained will be used for estimating x, with that warning that the successive approximations have not converged. So, the output as mentioned earlier, estimated value of x equal to xc and successive approximations s0, s1 up to sn. These are the outputs that we are going to get out of this algorithm. The time complexity, if you try to compute for this algorithm, then the worst time complexity normally we talk about of this algorithm is computed under the assumption that I loop is executed for maximum number of iteration minus 1 times, and hence depends on the choice of maximum number of iterations that we consider. The time required, because this is worst time complexity. In the best time complexity, it is possible that you may converge, algorithm may converge much earlier and the time required may be very less. But usually we compute the worst time complexity, and therefore we assume that algorithm will continue up to the maximum number of iterations, and that is how the time estimate will depend on its maximum number of iteration, choice of maximum number of iteration. So, time required for computing all forward differences will be, because there will be n into n plus 1 by 2 forward differences and only one difference you have to take. So, that will be a into n into n plus 1 by 2, where a is the time required for one addition or subtraction operation. Time required for computing S1 to Sn will be 3n into n minus 1 by 2, because that will be three terms we are using, into m plus a and plus n minus 1 into c. So, n minus 1 comparisons will have to be done, because every time you get into estimation, you compare that whether the previous estimate is same as the final estimate or not, and therefore n minus 1 into c, and 3n into n minus 1 by 2 plus 1 into m plus a will be required to compute that the entire sum on the right hand side. That can be observed by looking at the algorithm and looking at the for loop, how many times that for loop will be executed and all that. So, we can get that estimate clearly as 3 n into n minus 1 by 2 plus 1 into m plus a, because there will be one multiplication and one addition involved there and plus one comparison. So, n minus 1 times when you run it will be n minus 1 c. So, time required for computing Sn plus 1 to S maximum iteration. So, that means now here we are finding out only n number of terms only. So, we will now considering it will be 3 into max iter minus n into m plus a plus max iter minus n into c. So, that means the remaining number of algorithm, the remaining number of terms will be requiring only this much time. So, time required for computing xc will be equal to m plus a plus c, because that is only one multiplication, one addition, one comparison you have to do. So, total time required for the algorithm IIP dash MOSA is given by 3n into max iter minus n into n plus 1 by 2, n plus 1 by 2, not n into. So, it will be 3n into bracket max iter minus n plus 1 by 2 plus 2 into bracket m plus a plus max iter into c. You can simplify that and you will get up to this. And if you look at the asymptotic time complexity, then it will be of the big order O into max it. So, to summarize this module, in this particular module we have seen the technique of inverse interpolation. Initially we saw that why this inverse interpolation is required. Then we considered it as an inverse operation of interpolation, that means just by interchanging x and y. So, when your function is sort of 1 to 1, it is possible to interchange the roles of x and y in the interpolation and get inverse interpolation. But many cases this kind of function that you are that is involved, that gives the relationship between x and y may not be 1 to 1, and in that case we have to use more sophisticated technique for inverse interpolation. We have seen the graphical way to find inverse interpolation, and in that we have seen that when function is not 1 to 1, corresponding to 1x 1y, we may get several estimates for x. And if we really want to get more systematic approach for inverse interpolation, we have to use method of successive approximation. So, method of successive approximation was discussed, and then its time complexity was computed finally, and this time complexity estimates were given for the method of approximation.